Assalamu alaikum. Now let us focus on motion in two dimension, or 2 and 3 dimensions, but the simplest case when you have constant acceleration. As we have done before in motion in 1 dimension. So now we'll talk about motion in 2 and 3 dimension, but with a special case of constant acceleration. I think by now you are familiar with motion in 1 dimension with constant acceleration. If you remember this from previous discussions, in 1 dimension we had 5 equations of motion, and these equations, if you remember, V final equals V initial plus A multiplied by time t. The second equation was delta x equals V initial t plus 1/2 A t square. Third equation was V final square minus V initial square equals 2A delta x. Fourth equation, where the acceleration is missing, delta x equals V initial plus V final divided by 2, all multiplied with time. The last equation is similar to the second, which is delta x V final t minus 1/2 A t square. Let us try to see how do we treat with motion in 2 and 3 dimensions when the acceleration is constant. We'll use the same equations, but we have to notice these changes in 2 and 3 dimensions. These equations will look like the following. Equation number 1. Here, the velocity was in 1 dimension. Okay, so it was either in the positive x or in the negative x. But now it will be vector. So V final as a vector will be V initial as a vector plus the acceleration as a vector multiplied by time. So this velocity, final velocity, might have x component, y component, z component. Similarly, the initial velocity will have these components, all of them, or maybe 1 or 2 of them, depending on the problem. And the acceleration also might have 3 components, 2 components, or 1 component, depending on the problem. The nice thing here that we can write this equation into 3 components. The first component will be V final x equals V initial x plus AX t. So we'll treat the velocity along the x-axis alone, separately from the the y component of the velocity. So I can write it here, the other component, V final y equals V initial y plus AY t. Okay, the third component, if you can correctly guess, it will be V final z. So this is the z component of the velocity, will be the initial velocity along the z plus the acceleration along the z-axis multiplied by time. So nothing new here, but rather than dealing with a single equation in 1 dimension, now we can have 3 equations or 3 components of the same equation, equation number 1, equations of motion. Let me give you one more example, which is the second equation. Second equation here says delta x, now I write it as delta r, okay, equals, here V initial, I write it, but now as a vector, okay, time plus 1/2. The acceleration here will be a vector, and now this is the time square. This equation has three components. The first one, I can write it as delta x, okay, equals v initial x multiplied by time plus 1/2 ax t square. The second component along the y axis, and this can be written as delta y, will be v initial y t plus 1/2 ay t square. And the third component, I can write it as follows. This is the third component, which is delta z equals v initial z multiplied by time plus 1/2 az t square. And we can say the same for equation number 3, equation number 4, and equation number 5. We have to notice one thing here, that the time is the common physical quantity in all three components of each equation. This is very important rule, and we have to highlight it here. So notice that the time is the common physical quantity in all components of the equations. Okay, if you are talking about the x component, the y component, or the z component, the time is common in all of the three components of the equations. This will be clear in the example when we solve an example shortly, inshallah. Now let us take an example about the motion in two dimension with constant acceleration. So this is the statement of the problem. A particle leaves the origin with an initial velocity v equals 3I plus 4j meter per second, and has a constant acceleration. This is the acceleration given in unit vector notation, minus 1I minus 0.4 j meter per second square. Let us highlight few points in the statement of the problem. You see, the particle leaves the origin, so the origin means the x coordinate equals 0, the initial x coordinate is 0, and the initial y coordinate is also 0. So it is 0 and 0. The motion is clear to be in 2 dimensions, not in 3 dimensions, because the velocity has initially x component and y component only, and the acceleration has x and y components only. So the motion is two-dimensional motion. So this origin means 0 and 0. And initial velocity, so we should put here, this is v initial. We understand it from the statement of the problem. And the acceleration is minus 1I minus 0.4j. Okay, so this is the statement. What are the requirements here? Let me start with A. What is the position vector when the time equals 4 seconds? So when the time was 0, my particle was at the origin, was at 0, 0. Now we would like to know, where is my particle when the time becomes 4 seconds? Okay? Yeah. You notice something also here, that the acceleration is constant. And he said the constant acceleration, and it's clear that it doesn't depend on time. Here we have only a certain number. There is no time. If it depends on time, in that case, we cannot apply the equations of motion which we stated earlier. Okay? So what is given here? I would like to find what is the position vector. So he is asking us to find R final. This is the requirement. He is asking about R final. Okay, so R final, as we know, is x final I hash, I hat, plus y final j hat. Okay, so this is what we want. So basically, we would like to find what is x final and what is y final. Okay, so let me work out for the x final first. So x final would like to know. Okay, and y final also would like to know. What is given for the x direction? I'll treat the x direction separately from the y direction. Okay, what is given for the x direction? We know that x initial is equal to 0 because it was at the origin. Okay, and we have that v initial x, the x component of the initial velocity is 3 meters per second. Also, we have the acceleration in the x direction given to be -1 meter per second square. This is the x component of the acceleration. And he gave us the time. So time is given to be 4 seconds. Notice that we have the unknown, which is delta x. We have v initial x. We have the acceleration in the x direction, and the time is 4. So I have 3 known quantities, and I'm looking for the 4th. And this is the situation which we deal with in our equations. So let me use another color to solve for this. I have the time, I have the acceleration, and v initial is given, and I'm looking for delta x. So which equation should I use here? I should use the equation which doesn't have v final. So we have to use equation number 2, the second equation, which says that delta x equals v initial x t plus 1/2 ax t square. Okay, so this is x final minus x initial equals, of course, x initial is 0 because it was at the origin, and v initial x is given to be 3 multiplied by 4 minus, because here the acceleration is -1, so this is -1/2 multiplied by 1, t square, which is 4 squared. So I am left with x final equals 12 minus half the 16, which is 8, and this will be 4 meters. So it is 12 minus 4 meters. This is the final x. The acceleration is -1. It's okay. So this is x final. Let us now work the same for the y final. What is given? Y final is unknown. Y initial, it was at the origin, so it was 0. V initial y is given to be 4 meters per second. The acceleration in the y direction is given to be minus 0.4 meter per second square, and the time is 4 seconds. And this is what I told you before, that the time is common in all components of my equations. Okay? Similarly, we will use equation number 2. Use equation number 2. Equation number 2 says delta y equals v initial y t plus 1/2 ay t square. Okay, and here I have y final minus y initial. Y initial is 0, it was at the origin. V initial y, which is 4, multiplied by the time, which is also 4. Here the acceleration is negative, so I have minus 1/2 multiplied by 0.4 multiplied by 4 squared. And I am left with y final equals 16 minus 8 multiplied by 0.4, and this will be 3.3 3.2, and I am left with 12.8 meters. This is y final. He was asking me about the position vector, finally. And the position vector, as we wrote it here, x final I plus y final j. Now I am ready to write that position vector. So r final, I will write it as x final, which is 4 meters in the I direction, plus 12.8 meters in the j direction, and this is in units of meters. So we have answered the first question, or part A, about the position vector at 4 seconds. Okay, you notice in part A that the position vector turned out to have positive x component and positive y component, and this means that our particle is located in the first quadrant at t equal 4 seconds. The time 4 seconds, my object is having a positive x component, positive y component, so it is in the first quadrant. Let us move to part B. Find the velocity at time t equal 4 seconds. We know the position. We want to find what is the velocity. Okay, so the velocity, he is asking us about v final. Okay, so v final at t equal 4 seconds, where that was v initial when the time was 0 at the beginning, and now he's asking about v final. V final, we know it has 2 components. It has x component, so v final x in the I direction plus v final y in the j direction. So we'd like to calculate what is the x component of the final velocity and what is the y component of the final velocity. So I have to treat the x component separately from the y component, as we have done in the previous part. Okay, so v final x is unknown, but I know v initial x, which was 3 meters per second. I know the acceleration in the x direction, which is minus 1 meter per second square, and the time is given. Okay, so the time is 4 seconds. You notice that I have 1, 2, 3 known quantities, and the fourth quantity is unknown. So which equation should I use here? I should use the equation which doesn't have displacement. So this will be equation number 1. So use equation number 1. So here v final x equals v initial x plus axt. Everything I have here except v final x. So v initial x was 3, then minus 1 multiplied by 4, and I am left with v final x equals minus 1 meter per second. So the x component of the velocity is negative, and it has magnitude of 1. Now we'll do the same for v final in the y direction. So v final y is unknown. Would like to find it. V initial y is given. V initial y is 4 meter per second. The y component of the acceleration is given, which is minus 0.4 meter per second square. And the time, as we know, is common for both components, x and y. It is 4 seconds. 1, 2, 3 known quantities and 1 unknown, and we'll use similarly equation number 1. So v final y, v final in the y direction equals v initial y plus ayt. This is unknown. V initial y was 4 minus 0.4 multiplied by 4. So this is 4 minus 1.6, and this is 2.4. meter per second, and this is positive quantity. So V final Y is positive, and it is 2.4 meter per second. So the final velocity has two components, so I can give my answer here, plug it in this formula. So V final is nothing but -1 in the I direction plus 2.4 in the J direction, and the units, always don't forget to put the correct units. So this is the answer for part B. He's asking about velocity, and the velocity is a vector, so I should give it to him in vector notation. Okay, next part, he's asking about the speed. Find the speed at time t equal 4. We know the velocity. The velocity was -1I plus 2.4 J. The speed at that moment will be the magnitude of the velocity. Okay, so the speed is a scalar quantity, and it is the magnitude of the velocity at that time. So speed equals the magnitude of V final. From our study in chapter number 3 related to vectors, the magnitude of any vector is the square root of its x component squared plus its y component squared. So I am left with square root of the x component squared. So I have -1 squared plus 2.4 squared, and this is equal to 2.6 meter per second, and this is the speed of my particle at t equals 4 seconds. By the way, the speed is always positive, okay, because it is the absolute value or the magnitude of the velocity vector. Okay, because in mathematics you have studied that the square root can have positive and negative, but we will choose only the positive quantity. Part D of this comprehensive example, find the average velocity between time t equals 0 at the beginning of the motion and t equals 4 seconds. Okay, let us use the definition of average velocity. We defined the average velocity, V average, I am talking about average velocity. So this is nothing but delta R, the displacement, by delta T. What is the displacement? Displacement is R final, okay, minus R initial divided by delta T, which is T final minus T initial. Okay? But what was the position vector at the beginning of the motion? He said the particle was at the origin initially. So R initial is 0. It has X component of 0, Y component of 0. So R initial is equal to 0. So I am left with R final divided by delta T. So what is R final? We found this at the beginning in part A. R final, it is there, 4I plus 12.8 J. So V average will be R final divided by delta T, but R final is 4I plus 12.8 J divided by 4. If we divide, we'll get V average. The average velocity will be 1 in the I direction plus 3.2 in the J direction. This is the average velocity, and the units are meter per second. So this is the answer for part D. Let us take one further step for this comprehensive example. What is the maximum x coordinate reached by the particle? Okay, let me explain this question first. You notice something here, that my object initially has a positive velocity. Its velocity is having positive x component and it has positive y component. But the acceleration has negative x component and negative y component. So what will happen to this positive velocity? We learned before that if the velocity and the acceleration are in opposite direction, what will happen to my object? It will decelerate. Okay, so we have positive 3. Let us talk about the x-axis. It has 3 positive component in the I direction, but the acceleration in the x direction is negative. So this will decrease with time. So this quantity or this x component will decrease with time because I have opposite sign for the acceleration and the velocity. Similarly for the y component. So my object was moving in the positive x direction, but decelerating. It means it will reach the maximum x coordinate when its x component of the velocity will be equal to 0. Then it will change direction. Okay? So this is very important to notice. Maximum x coordinate will be achieved. Coordinate. This implies that v final x should be equal to 0. In other examples or other questions, he might ask you, what is the maximum y coordinate reached by the particle? In that case, you have to put v final in the y direction should be equal to 0. This is very important rule you have to recognize. Okay, so maximum x coordinate at that point, v final x will be 0. He's asking me about x final at that point. So x final would like to know. Okay, x initial we know it was 0. X initial was 0. V final x is 0. V initial x we know it is given 3 meter per second, and we know the x component of the acceleration, which is minus 1 meter per second square. Okay, so I have 1, 2, 3 known physical quantities, and the fourth quantity, which is delta x, is unknown for us. So which equation should I use here? I need the equation which doesn't have time. Okay, which equation of motion that doesn't have time is equation number 3. So we have to use equation number 3. What does it say, equation number 3? It says v final x square minus v initial x square equals 2ax delta x. Okay, v final x is 0, it is given here. Okay, so I have minus v initial x is 3 squared equals minus 2 multiplied by 1, because I have acceleration is minus 1, multiplied by delta x. Okay, so I am left with the following. Delta x will be 3 squared, which is 9 divided by 2, and this will be 4.5 meters. But delta x is nothing but v x final minus x initial equals 4.5 meters, and this x initial was 0, so I am left with x final equals 4.5 meter, and this will be the maximum x coordinate. Why is it the maximum x coordinate? Because at that point Vx is equal to 0. So after this, what will happen to the x component of the velocity? It will be negative. Okay, and you notice here at time t equal 4 seconds, at a later time than this one. Okay, we notice that Vx is a negative value. Okay, so here the time is less than 4 seconds. We can find the time. At what time this will happen? Okay, so let us increase one more. E, A, B, C, D, E, F. At what time does or is the particle at maximum x coordinate? Oh, this is a very good question. So my question now is very comprehensive. It covers many ideas. So let us answer this.